Okay, so if you have been staring at pages of logic gates and massive Boolean equation and you are very overwhelmed, then you're welcome to the right channel. We're going to demystify these heavy exam stress questions to a satisfactory puzzle. So let's jump right into it. Okay, think of this explainer as learning a completely new language. We'll start up with the language of ones and zeros. Then, like just like the alphabets, they will move over to meeting the logic gates, which is the vocabularies, and we'll learn some rules of Boolean algebra and the Morgan theory. Finally, we'll simplify the logic gates. Okay, we are here in part one, which is the basic of binary. So now in the basic of binary, we are looking at what is the basic values that we have in this Boolean algebra, and which is the zero for false and the one for a true. So this is the basic two values we have, unlike the normal natural algebra that have x for different values. This one is just 0 and 1, which is off and on. So now, how does this off and on translate into actual real life, steps or real life attacks? Now, the zero stands for off in the digital circuits, and the one stands for on. So that's basically how it translates. So every zero means off and or false, and the one means on. So now for part two, we meet the logic gates. The logic gates. So what are the logic gates? Now the logic gate is simply the building block of any electrical circuit. So now we have in this chart the AND gate. So this AND gate now, there are two inputs, and the two inputs can only give an output of 1 when the two inputs are ones. If you check the first row, you see that the 0 and 0 will give you 0 because no one is even 1 at all. Then the second row is 0 and 1. Even though there is a 1 there, it will still give you a 0 because one of them is a 0. Then the third is 1 and 0, same thing. But the last one is 1 and 1. So only when the two inputs are high, that is when it will give you high. And high stands for 1. I've told you before, 1 is high or on, while 0 is low or off. So that is how it works. And that brings about the name AND. So if input A and B is 1, it will give you 1. Otherwise, it will give you 0. So we'll move over to the OR gate. The OR gate now is even if one of them is not a high, but the other one is a high, it will still give you a high. But if both of them are not high, understand, it will give you a low. So we'll have the first row, 0 and 0 is 0, none of them is high. But the second row, 0 and 1, so one of them is high, so therefore it will be high. Then we have 1 and 0, so one of them is high, it will still give you high. Then 1 and 1, both of them are even high, so it will give you a high. So that brings about the name OR. So if if A or B is high, it will give you a high. So then not is just an inverter. You understand? It has a triangular looks and with something like a bubble at the tip. So we have 0. If you put in 0, it will give you 1. If you put in 1, it will give you 0. So if you remove that the inverter is that bubble. If you remove it from it, it will no longer be a NOT gate, it will be a buffer gate. It will not translate anything, it will not like invert anything. But that bubble makes it to invert. Then if you look at your hand, look like a very big D. That your AND gate. For you to remember it easily. Then your OR looks like a moon-like shape or a shield. So that is that for that. Then for the logic gate of NAND and NOR, we have the opposite of AND for NAND. NAND means not and, meaning anything that AND will give you. So the simple way to think of it is anything that AND will give you, invert it, turn it upside down, you will get the NAND. So 0 and 0 in AND is supposed to be 0 because none of them is high. But because of its NAND now, not AND, it will now give you opposite of that 0, which is 1. Then for 0 and 1, It's supposed to give you a 0 because it will only give you a 1 when both of them are what high. But now it's 0 and 1, so one of them is not high. So it's supposed to give you a 0. But now because it's a NAND, it will give you a 1, opposite of that. The same thing for 1 and 0. It's supposed to give you a 0, but now it will give you a 1. Then the 1 and 1, which is when both of them are high, that's supposed to give you a high. It will not give a low, which is opposite of what AND is. So I repeat again, NAND means not AND. So anything that AND will give you, just invert it. Like do the opposite. The same thing with NOR. NOR means not or. So 0 and 0 is supposed to give you a 0. It will give you a 1 because it will only work for high only when one of the inputs is high. But now both of inputs is low and yet it's still giving a high because it's not or. Then 0 and 1 is supposed to give you a high because one of them is high, or it will still give you a low. The same thing with 1 and 0. It's supposed to give you a high because one of the inputs are high, but now it will give you a low. Then for 1 and 1, which is even more prone to give you 1 because both of them are now 1, so it's supposed to give you what, a clear high. But now because it's not or, you understand, it will give you a low. So if you want to make it easier for yourself, you can just draw the AND gate, then anything that the output will give you, just do opposite of it. You understand? Just after drawing the A and B, which is the input, the two inputs, then the output just change, invert all the things that was supposed to come out for AND, you get NAND. Then invert all the things that's supposed to come out for OR, you get what? NOR. So that's it. Section 3. So for section 3 now, we discover that we have some of the kind of rule of this Boolean algebra. We have the addition and we have the multiplication. Then under the addition, we have commutativity. So commutativity can be addition or multiplication. So in this case, we discover that if you put an input A and you take all of it with respect to B, that's A or B, it is the same thing as saying B or A. You understand? Then multiplication, if you have A dot B, it's the same thing as saying B dot A. So it's still the same thing, it's commutative. Then for associative law under addition, it's if you take A or open bracket B or C close bracket, it's the same thing as saying A in brackets or B, then close the bracket, or C. So it's still the same thing. Then multiplication, the same thing. A dot, you have in bracket B dot C close bracket. It's the same thing as saying A dot B or in bracket dot C. So it's just like the pattern of arrangement, you understand, does not matter in this associative law. That is the pattern of in which you put the brackets for the first two or the second two. It doesn't matter. Then for distributive law, it's just like in your normal algebra, opening of brackets. If you have A or B dot C, it's the same thing as saying in bracket A or B close bracket, then we have open bracket A or C close bracket. So the same thing with multiplication. If you have A open bracket B or C, it's the same thing as saying A dot B plus, that's or A dot C. So you just that's that for the law or the properties of what, the addition and the multiplication. That's under commutative, associative, and distributive. Section 4, we have the law of complement, which is under the Morgan theory. So you discover that the complement of the product is the sum of the complement. This is not a rocket science, it's not very difficult. It means that when you take the product of two inputs like A dot B, the product of it, is you take A dot B, then you complement it, you put a long complement on top of it, it is still equal to you writing A complement alone plus, that's all this time around, B complement. So it's just like when you break that long complement on the on A dot B, that's A and B. When you break that long complement on it, it will not be equal to you taking the individual complement of A and B and then putting all in between, that's plus in between. Then the same thing goes with when you complement, when you take the complement of the sum. You understand? That's if you take A or B and put a long complement on them, on both of the A or B, A on B, you have a complement covering the two of them. It's equal to you taking A complement only, then dot. B complement. So it's just like inverse. If it is for multiplication, that's dot, and you have a long complement, it will be equal to each of the individual complements. But now you are not having a plus, which is all. But if it is a plus that you have a long complement on it, if it will not be equal to you taking the individual complement. But in this case now, it will not be what, a dot, which is an and this is the truth table for the Morgan's theory. So it gradually tells you how that what we have said is correct, such that if you have A or B or complement, it is the same thing as saying A complement alone. You understand? And that's dot B complement alone. You understand? So the truth table for all the variables we are placed in this table, as you can see, and you will see that each of the case was satisfied, such that you see the places where we had A or B or complement, it will see the same thing as A complement and that's dot B complement, and the inverse, the opposite of it, still holds. Okay, we are in part 5. So now let's put all this knowledge together and simplify circuits like equations or algebraic logic equations. So now let us know how do we so simplify these massive equations. Let us jump into it and work out examples. You understand?
Okay, now for the question, we have this expression. So the first step is to factor out from here. We can factor out A and C because A and C is here in these two expressions. So we have A, C factored out. So it will remain B plus B prime, or not B, plus we have A, B, C prime. So from here now, there's a law that says whenever you have B and B, that's plus B prime, or any letter at all, whether A plus A prime or C plus C prime, because A can either be 1 or 0. So let's assume it's 1. The prime of it will be 0. So if you add 1 to 0, you will get 1. If you assume also that here is 0, the prime of 0 will not be 1. So 0 plus 1 will still give you 1. So anyhow you assume it, the summation of these two, that's a letter and its prime, will give you 1. So we'll have 1 here. So 1 multiplied by AC will still give you AC plus A, B, C prime. So we'll have A, C plus A, B, C prime. So we can still factor out A. If you factor out A, or let's come over here. So if we factor out A, we should have C plus A, okay, C plus B, C prime. There is also a law that when you have something like this, it will end up giving you this C will remain, then this B will remain, but the prime will go away. So this is the final answer of the simplification. Though in our subsequent videos, we will look at more of the laws. Like this is a law, this is also a law that I use, so to make it easier. Thank you.
And finally, we are in section 6. Now we are talking about final exam practice problem. So these are the problems you are likely to face in your exam. And how do we face this? We have state the problem as the first step. So the step to circuit design steps, that's how to design circuits. We have state problem, then check your variables, that's find numbers of the input slash output variable, then assign letter symbols to the variable, that's under the symbols, then we draw the logic circuit diagram, then finally we simplify the expression using logic Boolean laws. Then finally, you express, that's obtain Boolean expression from truth table. So that's how you can easily, use this. Okay, now here is a typical exam practice problem that you can get in your final exams. So we'll be wrapping up with what we have done so far for now. In our next video, we'll continue with this exam problem. You can try solving it out yourself and meet me in my next video. Bye bye.